Hi, all. Welcome to the presentation today. Uh, we're gonna have we'll be covering a lot of stuff on linear algebra and calculus as well. And if time permits, we will take a look at some of the programming applications that we might be able to run and see the outputs as well. As we speak, we will go through some of the stuff as well. So today we're going to primarily be covering the session in Tensorflow. If you guys already have come with either Jupyter environment or you have come up with Tensorflow Colab, Google Colab that you can leverage to run the applications of Tensorflow, that would be great. We can run parallelly as well, so that we can go over some of the mathematical applications as we are speaking about now. As you're aware, this book has been released, A Greater Foundation for Machine Learning Engineering. It has been released this month, in the beginning of this month, and it is available on Amazon. It is for all the data scientists and data scientist enthusiasts, as well as machine learning practitioners and senior data scientists, and deep learning engineers. All of them can leverage all types of algorithms, handling machine learning algorithms as well as deep learning algorithms in Python, R, TensorFlow, and PyTorch. Again, TensorFlow is primarily leveraged for mathematical applications such as linear algebra as well as calculus, and also a few of the other applications for neural nets, and a few of the neural network architectures as well. And primarily, if you're going for R, you can read through my book and go through some of the statistic algorithms, and then you can start actually implementing them in R. And PyTorch, primarily I covered on reinforcement learning algorithms, where you could get a good comprehensive overview of all the reinforcement learning landscape in terms of what are all the Bellman equations that you need to be familiar with in terms of mathematical equations, how the whole reinforcement learning works, what's the math behind these applications, how they orchestrate in terms of producing the outcomes in the reinforcement learning landscape. All of that you can actually check out in the book. And we will be covering reinforcement learning and PyTorch in another session. For today, we're going to be primarily dealing with the applications of mathematics in TensorFlow. That said, we're going to get started with this topic here. And as you can see, the book is available on Amazon, and you can also, if you have any questions, even after the session, please feel free to reach out to me on LinkedIn for any questions you have, and we will do the best to provide the answers that you would need. Okay, so here is how we're going to start this session. Is primarily we're going to be talking about origins of neural networks for deep learning. As we all are aware that there have been several architectures, that we have in terms of neural networks, and we have Boltzmann machines, we have restricted Boltzmann machines, autoencoders, convolutional neural networks, recurrent neural networks, generative adversarial networks for generating natural language processing, such as tools that we have come across, GPT-2, GPT-3. All of these are part of the generative adversarial networks. And this book will cover a lot of applications in natural language processing in Python as well. So as we are reviewing the literature of all the neural networks and deep learning applications over the years that we have come across, there are several types of applications that have been built. Initially, people started building the AI by hash coding millions of rules into the programming applications, and that actually has limitations, because you cannot break through some of the probabilities, and especially systems evolve and systems are kind of chaotic. And if you're looking at weather prediction systems, or you're looking at traffic patterns, pedestrian movements, you can't predict all of that, and encode all of these millions of rules that you would like to apply and expect that it is going to function the way it's going to function in terms of how it's going to have to react to a situation. Like, say, like there is a light as a traffic signal and pedestrian is still walking, and how the autonomous vehicle going to handle a situation like that, right? So those are the type of chaotic situations, complex environments. So that's why rule-based AI could not go much further. And coming into 80s, there have been several other types of applications that have come across here, and people started introducing slowly Bayesian neural networks and statistical algorithms, more applications to overcome the challenges we have come across with rule-based applications. And that's when, again, like if we take a look at in the recent times, in 2000, we have started deep neural networks. Earlier, there were only neural networks. That means like the number of layers that you can build in as part of the neural networks were quite limited. You can't add more than a few layers. But again, when the deep neural networks were introduced, that was just a few years ago, and that's when actually it was introduced by Geoffrey Hinton, and people started seeing the advantage of having so many more layers, so that you can have you can process a large volume of information that you want to process through the neural networks, and you can produce your outcomes in terms of various industrial applications that you want to build for chemicals or retail or life sciences, healthcare, automotive, aerospace. A number of other industries can actually leverage these applications, and we can also overcome some of the challenges with overfitting, underfitting, and back propagation. All of those challenges we can overcome and come up with dealing with these thousands of layers that are built in this neural network. We're going to take a look at some of the activation functions. So as we can see here, we have an input layer. We have a couple of hidden layers, and that's producing an output layer. So as we can see, we have some neurons connecting multiple nodes, and as this activation process, and it produces the output. So it's very important for us to actually be able to activate these neurons to be able to provide the outcomes that we are looking for. And again, it's important that we also stay unbiased in terms of initializing the parameters for neural networks. If you're going to assign a specific parameters, then it's not going to be scaling up well, because it's not going to give you accurate inference or accurate outcomes. So you want to initialize the parameter as something that is not something you're assigning yourself. It should be something that's automatically generated from the system, so that you can initialize those parameters. And again, as we spoke about activation functions, there are several types of activation functions that can be implemented for this. And we are looking at sigmoid function that you can apply, or you can also apply hyperbolic tangent function, or you can apply logistics function. Various strategies for activating the neurons. Each of them have a particular range that you can activate and form linear transformation or a non-linear transformation to be able to compute the value and activate it, so that it will contribute to the weight summation of the total you're computing in terms of producing your outcome. And again, there could be some error. Again, whenever we are activating these functions, it's likely that you may come across some error, and that's what we can. That's when the back propagation comes to the rescue to actually reduce these errors and be able to apply this and have most accurate outcome as much we can apply. Again, whenever you're activating these functions like sigmoid or hyperbolic tangent function or logistic function, you may come across some of the issues which we have been having for many years. Like, for example, you can experience vanishing or exploding gradient issues. That's why, like, you can also leverage another type of activation function, which is called ReLU, which is a rectified linear unit. And most of the programming languages have come up with a built-in function, which is already part of your package. Like, for example, you're going for PyTorch or TensorFlow, these are already built in. So you can leverage this activation function. It's going to produce a smoother result and outcome as opposed to activating these functions. You have to manually activate them. You have to write a little bit of code, and then you have to perform, the linear transformation for it, and that's when it's going to actually activate it. So that is why exactly, you would need, the ReLU function that you can leverage for this purpose. Again, as we can see here, let's say that we're going to create this input layer with Z1, Z2, Z3 neurons, and then we're going to actually add the weights, and we perform this weight summation process. So we're going to produce the weights for each of these nodes, and then we're going to produce the outcome. So let's say here we have Z1, Z2, Z3, and then we're going to have the weights C1, C2, C3, and then we're going to be able to perform any of the linear combinations that we spoke about and come up with a computing summation of Z1, C1, Z2, C2, Z3, C3, and so on and so forth. That would give you the outcome in terms of what exactly the predictable outcome we are looking for. Again, it could be reinforcement learning, it could be supervised, unsupervised, or any semi-supervised. There are several types of machine learning applications that we have. We can apply any of that. Again, here is the vectorized calculation. That's what happens in this, and in order to produce the outcome. And now let's get started with a little bit of introduction on TensorFlow to see how exactly we can leverage, the TensorFlow function. And TensorFlow again is a library that's part of Python programming language, and it has been in research for a while, and Google has outsourced it and open sourced it, and has completely made it available for all of us to consume it, so that we can run it on our own. Again, if you're running for enterprise applications, that's entirely another scenario. We'll have to talk about the TPUs and all that. But if you are interested in running some of the applications and see how it can be helpful for you, you can simply go to TensorFlow, and you can actually export the file, and you can start implementing it. Again, the way that you implement this is you go to either Jupyter environment, and you can start installing your TensorFlow on it. Again, I put an article on how to install your TensorFlow. You can go and install it in Mac OS or Windows or Linux, wherever you would like to install it. And again, if you are going to Google Colab, you have already a lot of functions built in it. Plus, Google runs already the TensorFlow in the cloud, which will have TPUs built into it, so you have faster outcomes if you're running on Google Colab. If you were to run it on your own Jupyter environment after your installation is complete on your operating platform, whichever it is, Windows or Mac OS or Linux, then you will have to actually be able to create a CUDA, and then you have to say, okay, here is my GPU for me to hook up and wrap the module in it and run your code on it. So that's how you can actually we're going to take a look at Google Colab program today to see how we can run these mathematical applications, so that you can get an understanding of how it orchestrates and works within the cloud computing platform. Again, the TensorFlow is primarily, the purpose of bringing this is for coming up with handling a lot of numerical computations and challenges we have with multi-grid algebraic methods, or We're also dealing with conjugate gradient solvers, fast Fourier transforms, and matrix multiplications, and a number of applications that you want to compute. And also, it is leveraged heavily by a lot of scientific laboratories for parallel computing processings with MPI, which is a message processing interface. You also need to write some code in C++ when you want to run your code parallelly, because it's going to have some communication between the C++ as well as TensorFlow in terms of how it passes the information so that it can assemble the results back and produce. So you're going to run this on chunks of multiple clusters of supercomputer and get your results back and assemble it, so that it's going to be much faster. So that, again, there's no limitation for this, and you have n dimensional arrays that are available with the TensorFlow, also known as Tensors. You might be handling the arrays in Python called package of NumPy. So so you call the arrays and you call here Tensors, but it's the same functionality. But again, you can run here on GPU. You're running it on a particular TensorFlow application. We're going to take a look at the type of applications we have here and the data types we have. So there are several types of data types we have. Here are some of the data types we can handle with. So that's why, as I mentioned, it's capable of performing large-scale operations in terms of building applications, scientific applications, as well as computing. Some of the hardest numerical computations in terms of operations, like we got float pointers. We have because people are moving away from vectorized operations and moving to float pointers for large-scale operations you can perform on your mathematical applications. You can take a look at what's the range it's going to accommodate. So there, you can go to tensorflow.org and you can find out each of this data type, how much it can accommodate in terms of the the numbers. So some of them are unsigned, so that will accommodate the magnitude and quantity in terms of, like, you can put a plus or minus and you have a range of values. So whatever the operation you're performing, as long as it can accommodate within that, you can go for that. And if you're looking only for positive outcomes, then simply you can go for unsigned integer. If you're looking for both, then you go for signed integer. So that will help you to accommodate both of your calculations there. So now we're going to take a look at tensors, and the tensors are primarily, you can leverage all types of data types we just spoke about earlier. And so we're going to take a look at scalars, vectors, and multiple ranked tensors. And rank 0 tensor is a scalar that represents quantity, measurement, and number. And you can have a mass, speed, temperature, anything you can represent with it. And that is primarily a rank 0 tensor. So it's like your particular tensor where you can have a simple measurement. It's a simple quantity. That's a rank 0 tensor, or it's also known as the particular scalar. And again, vectors are rank 1 tensors, and you can represent a list of values in it where you can have both magnitude and the direction as well. And it can be interpreted as a point in space represented by number mapping the point in space. And any vector can be represented. For example, here we're talking about 3, 9. So we can see on x-axis a 3, and on the y-axis 9. That means I can go with magnitude as well, and so that you can compute the operations. Coming to the rank 2 tensor, you can have, we're going to take a look at the programs. So briefly, how we're going to run this, and how we can compute some of the operations that we can have. So let's take a look at this here, and we just want to compute some values, and so primarily we're going to be able to run this here and import the TensorFlow package as a TF. So primarily what it performs here is it's going to take this library and it'll reference it in our code with TensorFlow. Again, so as we just spoke about, the various type of tensors that we can leverage here. So you can simply, create a tensor string and simply assign a value to it. In this case, this is going to be a rank 0 or a scalar tensor. As such, there is no array involved. It's going to be a simple, rank 0 tensor. You can simply assign a value to it. For example, in this case, define something like a rank 0 tensor, and then you can assign constants to it. Which is here. I just created a constant as 5 and simply assign it to it, and then print it out. And you can see here, whatever that I've written here, it's printing the text that I've printed here, as well as I passed a simple value to it, and we are able to print the value as well. And then we have the tensor we just created with a constant. It has the value assigned to it as 5. And so that's about the rank 0 tensor. Again, rank 1 tensor, what we're going to assign here is primarily, let's say we're going to assign few values like value 1, value 2, and value 3 here. And that will will tell you, what's the rank of this tensor. So here, after assigning this value to tensor rank 1, and then you can just simply print it out. And also you can pass some constant values into it this way as well. And then you can print it out, and then you can see the values here that are available for you as part of the rank 1 tensor. Again, rank 2 tensor, we can run the following commands to see the outcome of this particular rank. So, for example, in here, let's say we're going to create another constant. We're going to assign the values 3, 9, 1, 4, and 6, 8 here for this particular tensor. And then just run the outcome, and then you can actually see when you print it out, you can see the values that are being printed out here. And it's telling us the shape of this tensor is 3 by 2. It's a rank 2 tensor, but the shape is 3 by 2. What that means for us, if it's 3 by 2, right? So 3 by 2 is 3 rows and you have 2 columns. And when we created it with a float type of float pointer. So it tells us that is the data type we leverage for this particular application. You can see that here. And again, you can create another float tensor as well. And you can see the values coming up here. And in this case, we create another shape, 3 by 3. So it tells us you have 3 rows and 3 columns as well. And the other important thing is that, the shape, as we spoke about it, the shape of the tensor. So we see how the shape of tensor is created based on the number of elements that has in the list that it has. And again, so you can create as many type of tensors that you would want to create. And again, is it possible to change the shape of the tensor? So we're going to take a look at to see. So we saw that it's a 2 by 3 shape. Can we change the shape and make it a 3 by 2, right? So that's our question we have. So yes, it is possible in TensorFlow. You can actually change the shape of the tensor by keeping the product same, or you actually change the sizes. So your product is going to be the same, but you just change the sizes. So in this case, we're going to have, again, create another tensor 1 in this case. Just send some constant values into it, and primarily it tells us the shape of this tensor here is the values that we have created earlier. And so the number of the elements are how many total number of elements are there? The total number of elements in this are 8, and we have 2 nested listed at once. We can change its shape to multiple lists with 2 elements each, and then you can see that actually we're going to be able to reshape this tensor. So we have tensor 2, tensor 3. So let's say we're going to send a few values to tensor 2, and we're going to send a few other values to tensor 3. We're going to just simply print it out, and you can reshape the change. You can change and reshape the tensor as well. So those are the operations you can perform in terms of the tensor. So now coming to, let's say that we're going to perform a matrix multiplication. In this case, we're going to take a look at, how we can perform the calculation, and what are the outcomes you're looking for. You take any tensor rank 2 4 matrix and take another matrix which is of another 4 by 5 here, and you multiply them and you're going to get your outcome here. So if you were to manually operate, you're going to take, okay, 3 by 2 plus 9 by 1 plus so on and so forth. You can multiply like this manually. So if you were to manually calculate it, this is how you're going to calculate it: 3 by 2 plus 9 by 1 plus so on and so forth, and you're going to get your value like this. But you don't have to manually calculate. The TensorFlow performs a calculation for you, and then you can get your value calculated as a which is called primarily a dot product, which is a result of multiple matrices we have here. And again, the Moore-Penrose pseudo-inverse is another type of application we have. You can take a look at a YouTube video that's created by me earlier. You can take a look at that and see how exactly you can understand the math behind it and what's the purpose of this, and what type of corporations are leveraging this and how they can actually utilize it. You can take a look at that. And again, you can, if you get the book, you can get all of the information in it. That will help you to achieve your outcomes. So we're just slightly running out of time here, but we will try to quickly go over a few other applications here. You can go over Moore-Penrose pseudo-inverse. And so here I built an application to prove that it actually works. And if you get the book, you can get all the code as well, so you can perform some practicing exercises. And later probably we can create a workshop so that I'll be giving some exercises. You can parallelly get hands-on and you can start writing the code if you're running into syntax error, or you're running into any issues that I can help resolve the issues that you have, so that you can get your outcomes. That way you're geared up, fully ready for your for being a data science practitioner in the field of machine learning and deep learning as well. So again, this is something you can try to create a few samples for yourself and see how you can implement it. Again, the singular value decomposition is a billion-dollar algorithm. The reason why they say it is because many companies like Amazon and Netflix, they all leverage the singular value decomposition algorithm for building recommendation systems. So that's why this is called, because that's the the range of companies and corporations that leverage these algorithms. And this is not like something like is not in popular use. It is very effective. Every company uses. Again, people create their own customized algorithms. If you're going for regular algorithm, so this is what you can implement. But again, companies like this have created much in-depth algorithms, like creating more granular approach in terms of customizing it and be able to implement it. Okay. So you can implement this as well, and there is a YouTube video that I provided for you as well. There are a few other applications I want to share with you, but probably the spiking neural networks is another supercomputing. Many of the supercomputers like Spinnaker, all of them leverage the spiking neural networks, which is the next generation neural network for supercomputers. If you're especially ARM-based supercomputers with multiple chips, and then you can also implement spiking neural networks. You can see how they spike up, and then there's a supercomputer called Spinnaker that has been implementing the projects for the various applications. So they want to simulate how the neurons work in human brain, and so those are the type of applications they have built earlier. And in PyTorch, I wrote this application to actually create the spiking neural network, so we can see how exactly we can produce. So you can just see the output for now, for the lack of time. So you can see that all of them got activated. And again, I also ran through some MNIST data sets, which are for producing the numbers as the outcomes. So you can see that. Again, when you get the book, you can get all of this, and you can run through this applications, and you'll be able to implement a lot of applications for that as well. Again, we just spoke about this, and now we're gonna quickly go through some of the calculus functions we have. So again, calculus also holds a wider role in performing the numerical combinations in supercomputing, especially if you're building any applications for particle physics or aerodynamics, or any other scientific applications that you can come up with. You can actually leverage calculus, and also for training the neural network, there are a lot of calculus applications you can implement. As we spoke about, back propagation is completely running on in calculus. Many places you would be needing calculus, which is a prerequisite. So that's why I call it a greater foundation, because many applications that you build, a lot of people ask me questions. Instead of taking us to the advanced stage, I tried this before with another company called Pact. We produced some videos on reinforcement learning training classes, and a lot of people ask me, you're just telling us reinforcement learning, you're talking about Bellman equations, you're not getting the concepts on how we can get started in it, and how we can go forward with these calculus applications. Or they wanted to understand some of the algebraic fundamentals, so that they're very well prepared before they can go and implement some advanced algorithms. So that's the reason why I built this for you, so that you can go for all the fundamentals of linear algebra and calculus as well. So for example, as we saw, that if you're just simply implementing multiply, then you're going to get scalar multiplication. If you're leveraging a function like matmul, which is it's going to multiply like large size matrices that you can multiply with each other. Again, we also saw the other application just now, which is let's see here. If you're looking at this particular function, tf dot linalg dot svd, this is a built-in function that's part of TensorFlow package. So there are a lot of functions that you can actually leverage here, that whenever you're implementing, because it's also, there's a singular value decomposition. So here also, if you see where S, P, and V are the singular decomposition of A. So initially we perform the SVD for it, and then we're gonna perform a pseudo inverse of the P plus of a diagonal matrix P, that is obtained by taking the reciprocal of the non-zero element and taking the transpose of the resulting matrix. So since it involves that we have to perform this, so that's why I also have implemented the df dot linalg dot svd. So this is a built-in function, it makes your life so easier. See, the code is super crisp. You don't have to write like pages and pages of code. Just call the function and create your matrices and assign the values that you need to assign, and you're going to get your outcomes here. So that's the advantage of TensorFlow, where you have a lot of built-in applications, a lot of built-in functions that you can leverage. So that's why I'm telling you that it's important that we get equipped with all the fundamentals of programming languages, as well as fundamentals of math, linear algebra, and calculus, so that when you go for some advanced calculations, you would be able to actually implement algorithms for a project that you're working on. So that's the purpose of providing this for you, so that you can actually leverage these applications in your everyday life, that you can actually implement your projects. So that I want to extend this to all the people who are getting started, and they're more enthusiastic in terms of getting all the fundamentals of mathematics, so that they can be more equipped. Again, as I mentioned, like calculus is simply, we can say that it's a field that calculates the rate of change. So any rate of change for a function of x, fx with respect to a function of fy is called simply the calculus. So you have a Leibniz notation, and you have a Lagrange's notation as well. So you can take a look at that. So that's exactly what, as G. Leibniz said, that it's a study of continuously changing the quantities with infinite process with a notation of limit that reaches an ultimate value in the mathematics. So it is a field to signifying the rate of change in a function at a particular point. And again, so we also have automatic differentiation. So automatic differentiation is again another aspect of calculus where you can actually implement it. And you also have some of the built-in functions in your programming language, for example, in Tensorflow and also in PyTorch that you can actually leverage. So previously, many years ago, people have to compute it manually, and they have to, like if you are going in a forward mode differentiation versus, backward differentiation, you will have to write a lot of equations, and you have to write everything from scratch, and you need to write all of the applications. So that was a bit complicated. So now, considering that we have, a lot of people like Hamiltonian Monte Carlo sampling methods and training the neural networks, all of them leverage this automatic differentiation. So wherever you are, at what stage of project or in your journey of data science, you can take a look at it to see how you can implement it. Again, as I spoke, here is a forward differentiation, and here is a back differentiation, forward mode and backward mode. So it works in both, and you can leverage the automatic differentiation package that you can implement in math for calculus. Again, there's a matrix calculus by itself, which is a separate, a branch of calculus. And, I don't want to combine that with linear algebra, because matrix calculus is, I would treat it as a part of calculus, because, Jacobi in 1835 has invented, the Jacobi determinant, and he also has introduced and proposed the matrix calculus. And you want to go through the matrix calculus, how you can create a differential of each function, and how you can calculate all of that. And I explained the inner workings of automatic differentiation works, and how you can create all of this for your mathematical applications in TensorFlow. I have created some programs that you can go through and you can run through, and you can create some exercises and perform this so that you're completely familiar with, gradient tape API is another function of TensorFlow that where you can actually go and, kind of find all the, this is like a recording. So it will record all of your operations of mathematics that you performed, and then you can go back and play back. You can see exactly where, at what point of time, what was the change that you implemented on this variable, and what is it now. So you can take a look at the whole thing with gradient tape API. So that's another API that's very interesting for calculus as well. And again, chain rule is a very common function we implement for training the neural networks, and we can create a composite function for that, and we can apply that for obtaining the differentiability for the function that we can create. Again, you can run these exercises, because I just conducted another conference like a few weeks ago, where I had taken like the 5-hour session, where I actually was able to participate in the workshop, running each piece of code and trying to understand where people had issues, so we can work together and resolve those errors and see how we can progress forward. But today's session is going to be, we're going to just be running some programs, and we'll be reviewing mathematical applications and the programming methods and APIs, what we can leverage. But another session where we can have more longer, we can actually run these applications, each of them. That way, you're going to be more benefited. Again, here I try to also explain how the back propagation works. Again, back propagation is now a function in many of the programming libraries. But again, I want to explain, that's why I have taken this example of back propagation here, to see how we can actually achieve this, just simply explaining how it works, the math behind the back propagation here. So as we can see here, we have a neural network, and we have assigned some initial weights. Again, as I said, we're going to initialize the parameters. We're not going to assign something that what we like. It's going to be, whatever the system generates automatically at runtime. So that way we're going to stay biased, and we are also going to create a couple of bias nodes here, and we're going to optimize the weights. And here we're going to take so we initialize the weights, we assign some initial parameters, we're going to take a forward pass to it and compute the total input assigned to each neuron and apply the logistic function. So as we spoke earlier about sigmoid function as well as hyperbolic tangent function, in this case I'm applying a logistic function here. We're going to activate the neurons, and we're going to compute the total summation of it. So here, as we can see, the net input. So this, I'm just multiplying the weight that is calculated by the input neuron, A1, and then multiplying the rest of the other weights of the A2, and also taking the bias node and the corresponding weight as well. So that will give us the net input. And again, I'm also computing a net output here. So that's the net output for A1. This is the net output for A2. And then again, I'm computing a net output here for the overall Z1, which is a result of weight summation of these neurons here. And again, you continue applying this process by applying the logistic function. And then you will keep getting more values and more net outputs. And here you can see, this particular net input for Z2 as well as, so here is our endeavor to calculate this particular error that we're getting in this weight summation process. So if you take the total error and compute the error here, so that's coming as, this is the error we are getting here. And then we can apply, a chain rule to it, and we can, get more outcomes onto it. So here is the value we're getting for this. The output is 0.74. So you might be wondering, I mean, this is all the accuracy we have improved on this overall neural network. No, but you can actually, you may see this when you run multiple episodic iterations, you're going to be able to resolve this, and you can actually improve in terms of how much error you can improve it all. Like for example, reinforcement learning, you run a lot of episodic iterations where each iteration is going to reduce, but then again, overall, it's going to, be a huge improvement in terms of optimization of, the overall neural network outcome. So I will now, any questions or anything we have, we can take a look at that. And, please feel free to ask any questions that you may have. And also, again, you can reach out to me from LinkedIn. If you have any questions, feel free to send a message, and I will certainly respond to you on LinkedIn as well. So if you have any questions now, please feel free to bring up those questions.